Welcome, guys. Thank you for coming to our weekly speech and NLP tech sharing. Today, we're going to be trying to deducting OpenAI's GPT-4's neural network architecture. And this is our YouTube channel's barcode, and this is our meetup barcode. And it's published on May 13th, 5 days ago. It says, OpenAI says, GPT-4o, their new flagship model, it can reason across audio, vision, and text in real time. And I guess everybody has seen the demo. It is awesome. But this time, there's no archive paper, there's no technical report, and there's not even a clear illustration of what their capabilities. When I'm reading their introduction or the description of their model, something came into my mind. I think I can, not to say deduct, or I can try to guess for you guys, what is the possible neural network architecture for GPT-4, because I think it's very important for these large intelligent language models or multimodal models to be open. And this is important for the development for the AI community. And I think OpenAI is becoming closer and closer, or it's being like a safe box. Okay, it doesn't want to tell other people what they're doing. So you can see in their description, one thing they mentioned is very interesting. It can respond to audio input in as little as 232 milliseconds with an average of 320 milliseconds. Of course, those numbers are very impressive. But as somebody who has been working in the speech domain for many years, these mean something. I guess you guys, some of you have seen my videos. I have explained you what the normal architecture of ASR is. You can see they're not using any structure like their Whisper anymore. Because if you have seen my Whisper video, Whisper always take a chunk of 30 seconds of audio, and it has to wait the input to be finished. So that literally means that this means if they use Whisper model in their GPT-4o, that means they're still using the previous cascaded system as they mentioned on their website. So they're doing some new voice mode. It's not just Whisper. And some people ask, okay, wait, is this RNN transducer? No, it's not. Let me tell you why it's not. If you're using RNT, because RNT is time synchronous decoding, they won't talk about the average, because if you're talking about something average, that means sometimes it's fast, sometimes it's slow, right? So they're not using some architecture like RNT, which guarantees the latency, okay? If they use RNT, they would say with an latency of some milliseconds. There will be no average this number, okay? And then you can see they're still adopting some type of autoregressive decoder architecture in their networks. And here you go. No bullshit. I will come directly to this architecture I deducted based on their description, their demo, or from what I see. Here you go. Where do I start? Okay, let me start first off with the encoding part. Like they said, this model is ominous. It can take audio, video, and the text as input. Let's suppose, so definitely this model can work with the traditional input, which is text only, right? So when you have only text as your input, so you start off from here, you pass the text through a tokenizer, you get some text tokens, for example, or a sentence of text tokens. Then you send your tokens into the LLM decoder. Then you get a text token, right? Then you feed the text token back to the input and shift everything one token to the right. Then you get the next token. Then you keep doing this, right? So this is how they call it autoregressive decoding. And inside of the LLM decoder, it's a stack of transformer decoders. There's only self-attention involved. There will be no cross-attention. Of course, there will be positional encoding. So this thing, everything, OpenAI optimized this heavily, so they can run very, very fast. So let's see when they have an extra model as input, which is audio. Okay, I'm specializing in audio, so I know what they're doing. So the difference from audio to text is audio is always a stream. It's not like a text, it's just a one snippet, that's it, right? The audio can keep being fed into their model for hours, okay? Because you can see that during their demo, they're keeping talking with their audio and they do not stop or pause or something, right? So this is I shown here at the time t equals 0. They have a feature extractor or input windowler. It will crop a segment of audio as input. This audio segment down below here. And once you have this audio segment, it will send you into audio encoder. So I believe that they train everything from scratches, okay? They train, but if you say, if I want to do it, what I should do, I would recommend you to use the Whispers model's encoder as a initialized encoder. Make sense? And then you get audio features, or called audio embeddings. And then you pass through an audio language connector to convert these audio features into audio tokens. Why do we have to do this? Because audio features is in the continuous feature space. You want to map this to a discretized feature space, aka the token space, as the text tokens fed into the model, okay? So once you have the audio tokens and text tokens, so this time, if you're just talking to the model, okay, this time there will be no text tokens, right? You won't have audio tokens. For example, the audio tokens has 128 tokens. Then the difference is that the LLM decoder was still accepting these audio tokens as input, but these LLM decoders is no longer text only. Okay, everything is retrained on these audio, video, and text, or optionally audio only, text only, or video and text only. This type of kind of input. So they trained a multimodal LLM decoder. So the decoder is capable of outputting a text token whenever you send a input tokens. That makes sense? So once you get the text tokens, okay, of course the text token would be fed into here, and you can wait for next tokens input. to be fed into the LLM decoder. And you ask, so how do you get the next audio tokens, right? Okay, because for the next time step, for example, t equals t1, the window shifted, for example, like a 0.1 second, okay? And what's the audio tokens? And what are the text token? Of course, text token is always the output text token being fed here. And when the text token is that you shifted the window, you get a new audio segment. And the interesting thing is that you also have a prompt part. The prompt part is a accumulation of the historical text tokens. So this is exactly the same as they do in the Whisper model. The Whisper encoder has a position for you to send into the historical decoding results. Okay. Then you can see the audio encoder can take prompts and audio segments as a Whisper encoder. Then it does the same thing and get the new text audio tokens and combine with the previous text token, send it to the LLM decoder, and you get a new text token. Then you keep doing this. It is called autoregressive. And you say, okay, wait, they're not just outputting text on the cell phone, right? They're outputting speech, or is a humanized voice, right? So that step is super simple. That's a separated model. I believe, that's what I believe. I believe they're still using a cascaded system because they're saying that in their website, they're saying that they only give you 6 voice choices. So that means this voice has nothing to do with the user's voice. So it's a separated system. So the audio decoder, or some people call that, or our speech people call that, speech synthesizer, will take the sequential text tokens as input and outputting audio segments. Then you, in the end, you concatenate these audio segments to get continuous audio output stream. That's what you hear. Okay. And you can see, I have seen they work on solving math equations. Remember, they just posed a cell phone camera to 3x plus 1 equals to 4 and trying to ask GPT how to solve that equation. And they have some interactive stuff. Then you should look at their video encoder. So everything is the same. For example, every 0.1 second, they would get a video segment, get the features sent into the video language connector to map the video features into the token space. Then this time, they will have audio tokens plus video tokens as input into their LLM decoder, which is multimodal. And of course, this time, I don't think they have text tokens or text as input. They don't type while they are talking, right? They don't have text, but they will always have the previous text token from the last decoding step, okay? And you still get text tokens and you get audio encoders, then you got the text, the speech output. That makes sense? So I want to stress 2 points in the following. First is the streaming part. You said, okay, where you see, I understand you always have a sequential of segments as input, and the sequential of input segments are cropping from the streaming audio. I understand this. I want to mention the delay. So you can see that by doing this, for every audio segment sent into the model, you can see the LLM decoder would have to take either audio and the video input as a decoding step. So you can see that every step, every decoding output, it takes different amount of time. Makes sense? Because it depends on how sophisticated your audio tokens are, and whether you have a multiple model as input. So the latency is always different. Of course, the audio decoder, I think the latency is always constant or almost constant. And then you can see the delta here is the latency here. So everything passes through how long the time it takes to pass through this loop and get to the end of the audio segment. This is the system latency. And I would say that in terms of engineering, it's fairly impressive to me that it can minimize the latency of this whole process to a level of about 300 milliseconds. And don't forget that according to some studies, 0.3 seconds or 300 milliseconds is something that humans are very happy with. Or if how to say this, if the latency is less than 0.3 seconds, lots of people won't notice that. Okay. Of course, I think GPT-4o is having way much latency than that. Why? Because there's a network latency. Okay. I think what you're talking about is just their network latency, not their overall latency when you're using it. Okay. The next thing is what kind of data they're using to train their multimodal model, or how to say this. How do they organize their data into training this model? Of course, let's look at the very easiest part, the audio decoder. It's just sending the text tokens and getting the output speech and compare some type of MSC error or what type of cross entropy loss. Okay, this is trained separately, and I believe the audio encoder, video encoder, and tokenizer don't have to train. Tokenizer can train separately, of course. But the audio encoder and the video encoder plus the multimodal LLM decoders, they're trained jointly. And the training would have two stages. First is the unsupervised learning stage, and the second part stage is the supervisor fine-tuning stage, and they will probably have a instructed fine-tuning stage. Okay. In terms of the data, I would assume that they would be heavily leveraging the conversational data. Let's think about what type of data conversation data has. It usually evolves with two or more people. One is the user, one is the respondent, or one is the prompter, or one is the asker, one is the respondent. You can see once you have the audio and the video as input, and you know how to say this, because you're not, first you train that unsupervisedly, right? That's simple, right? The second step, you do the fine-tuning. The fine-tuning part is you would use the user's audio or video input as the input to the model, but over here, when you compute the cross entropy loss, you would be using the system's response as the output. Okay, and this can explain why the system can have the interruptive feature as our normal human being. What does that mean? It means if I say something, then the system understands what I'm saying. So even I'm saying that I'm still saying something, the system can hop in and interrupt what I'm speaking and start to talking about what they are thinking that's important. So this is very simple. As long as you have the training data, so you know the training data will tell you when to interrupt and what to interrupt. So for instance, at the T time to T1, the system tells, okay, here is the time I should interrupt. And then it will output the text token and start to generate TTS response, okay? And on the user side, a user would be listen, or the user heard, okay, the system is start talking. So for lots of time, we will be cooperative, you know, because when somebody interrupt us, we usually lower our voice or stop talking and wait it to finish, right? When it finished, you can see the system doesn't have any input. Okay, the user would think, oh, here's my turn to talk. Then it will start to talk again. Then you get the text token again. The system would be at the very beginning, when the person is talking, the output text token is usually null or nothing, right? You should be waiting for the user to finish, or as long as you should know what the person is talking about. Once the system knows what they're talking about, the system can hop in and start to generate audio again. Make sense? So I think that's the two important things I want to stress here. First is the latency of their system. The second is how they organize their data. I think I'm going to be stopping here. I'm definitely would want to mention one of the papers that I have read before, which is Apple's MM1 model. It's a multimodal model. I think the reason I can deduct the GPT-4o model is because I have read this paper. This paper is fairly good. You should read it. And at last, we're a company, we offer data solution. We can curate text, visual, and voice data sets. And we can also auto-label your proprietary data for training your vertical large language models, ASR models, and TTS models, or even multimodal models. We can also offer services. We can help you to, or assist you to build your own in-house ASR, TTS, and other speech-related applications. Scan the barcode if you're interested. All right, I'm gonna be stopping here, and thank you for being with us. Please don't forget to subscribe to our channel and hit the notification bell. I will see you next week.